Kurt, I just want to go over something real quick. So this is my final answer. It's my final proof, and I can put it down on a piece of paper and send it into the Clay Maths Institute. But I don't really care. You can't send it into them. You have to get it peer reviewed. But anyway, this is the tiniest proof for P equals NP that I could come up with. Ready? Rainbow tables for 3 sat is my premise. And my conclusion is P equals NP. QED. This is given an axiom that the rainbow table is a polynomial time lookup based on input length. Anyway, that's my proof. I'm still pissed that no one will take it. Like someone, I'm telling you how to win $1 million. Just steal it, making it really easy. If you need Theorem 3.16 in Introduction to Theory of Computation, you might need it. You can set up a little contradiction if they tell you can't have infinite Q. Because you're going to need infinite Q for a rainbow table for 3 sat. Anyway, I was looking up why does P equal NP on the internet, and of course I get a picture of P not equal to NP because y'all are fucking insane. But then I was looking at Stack Overflows, and someone said, as nicely laid out by Scott Ayerson, MIT, if P equals NP, then the world would be a profoundly different place than we assume it to be. I think that's true. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. And that's because they're under the opinion that and non-determinism is bound by your verifier and determinism is bound by your determiner. I don't know who came up with that, but what have you. I just find it really interesting. Like, the verification, both paths are open to you, right? So why can't you guess the verifier, but you can guess the determiner? It doesn't make any sense. It's just because you guys that's how the cards laid out. But I just don't understand if I'm gonna be omniscient and and guess the right answer because I have the answer available to me. I also have the verification available to me. So why can't I guess the verification too? I just don't get it. But okay. The verification is non-determinism and the determiner is determinism, whatever. But I just want to go over this quote because it is true in aspects. I think it just takes the wrong perspective on P equals NP. It says that there would be no special value in creative leaps. I would like to state that I'm a causal determinist, so everything that you do is determined by the causes, etc., so on and so forth. It's kind of like a recursive function enumerating itself. Like a Russian doll expanding or something. I don't think it would be a Russian doll unfolding. It would be a Russian doll growing. It's kind of what I'm on. But I mean, you could look at it as unfolding too. But anyway, because I'm a causal determinist, your creative leaps are determined. Like, there was a path that allowed you to get to that creative leap. For example, I would have never been able to prove P equal to NP if I hadn't taken computational complexity classes and gone to the school that I went to and been a trans man and realized that everyone has no fucking clue what's going on and it's just their best guess and they live in this system that's totally bullshit because it could be different ways, but we just decided to agree on this system. And we all want clarity and purpose, and a unified system gives us that. Um, but this there would be no special value in creative leaps. Creative leaps are very special because you were able to find a path that allowed you to get that to that creative leap. Unfortunately, once you do stuff, it's determined that you were doing it. So to say that once something is done, it makes it less special doesn't really compute in my head, at least. But once you've done something, it's determined that you've done it. So I guess it becomes less special because it's been done. And you can see this in once the first person does it, it becomes less special down the line. Um, it's just the first person that does it. It's special because that person was the first person that was able to determinedly do the special thing. But once it can be determinedly done, it becomes less special. So if you had a computer that knew all the answers to all of the proofs, it would become less special to prove a proof because it's already determinedly done by the computer. But that doesn't change the way things are. And I'm not saying that you can come up with a computer that can solve Bounded and Shining's problem today. Like, that's not what I'm saying. I'm just saying that the answer is the answer. And once you come to determine that, it's determined. And that's all. That's why P equals NP. Because of that. And non-determinism doesn't really get you anything unless your knowledge base is just as strong as the deterministic Turing machine. Because it's about the knowledge that you're operating under. If you have good knowledge, deterministically, you're going to make better choices than the non-deterministic Turing machine that has worse knowledge. Even if you only have one choice, you can only do one thing. If your knowledge is better, that one thing is going to be better than anything the non-deterministic Turing machine is going to come up with. Because of the knowledge. So it's based on the knowledge. And if you give a deterministic Turing machine all the correct answers to an NP complete problem, or a false answer if a correct answer doesn't exist, then the deterministic Turing machine in polynomial time could traverse and look up, find that answer, give it, and verify in polynomial time. That's all it takes. The determiner is the certificate is the determiner. You just have to do it once. Write it down. That's how you reuse time. You just write it down. Then you don't have to use the time to compute anymore. You just have to do a lookup. It's how humans compute too. It just makes so much sense. So when I look up why does P go to NP, I should be able to see something like this on Google, and not P is not equal to NP. Just because Stephen Cook decided when he was going to ask this question to beg the question and say that P is not equal to NP. Because P is equal to NP. Einstein was a strict determinist, and we need to come to this conclusion together so that we can implement the granddaddy of algorithms, which is just the answer. So anyway, knowledge is power. It's not money. I don't want your money. I just want people to start telling the truth. This is the logical way to go about things. P is equal to NP. I existed one machine. The machine just has all the answers. All you have to do is exist one deterministic Turing machine that can solve NP complete problems, and you prove that P is equal to NP. So I have done it. Congratulations, Kurt. I'm a genius. I'm a genius. I'm a genius. Apparently, someone wrote in the ACM that P is maybe equal to NP, and they had written lots of papers in the past that were saying that P is not equal to NP, but they said that it could be that traveling salesman problem could be proved in polynomial time, maybe with AI. I don't think AI is strictly deterministic because it's changing based on how it's learning. However, if you take an AI and allow it to grow the states that it can be in, then it is deterministic because the new algorithm represents a new state. But if you have to be in a finite number of states, AI is not a deterministic Turing machine. Even if you program a computer to do it, it's not going to be a deterministic Turing machine. But that's cool that you almost have a polynomial time algorithm for traveling salesmen. Um, I think that there is an equivalence, like I said, between deterministic Turing machines and non-deterministic Turing machines. I just think that you have to have infinite states to do anything really cool with it. Um, so, and yeah, traveling salesman's cool. It's just if you have a start point. So one time I tried to solve traveling salesman problems. So I'll give the real life example of when I was trying to solve it, and my father was like, "This is a problem that people are trying to solve in mathematics. You can't solve it tonight, Kurt." But I was trying to solve it in high school because my family was going on the Tacky Light Tour. And the Tacky Light Tour is a collection of houses in Richmond, Virginia that you can go to, and they have tacky lights for Christmas. And the problem was such that I wanted to leave from my house, hit up all the houses in the Tacky Light Tour, and end up back at my house in the shortest distance. And that's traveling salesman problem. How can I hit all of the houses in the Tacky Light Tour without revisiting any of the houses in the shortest distance and get back to my house? Traveling salesman. It's NP complete. My favorite NP complete problem is 3SAT. So if I'm talking about an NP complete, I'll probably use 3SAT. But just basically, if you have the answers, you have the answers. You don't need to have an algorithm. And I just existed one machine. That's all it takes. The answer is the answer. Congratulations, guys. It's really not that difficult. It's you're making it so much more difficult. And why I said that the AI probably isn't a deterministic Turing machine unless you break a bunch of rules is I think it's funny that all these mathematicians think they have to exist a real life machine in order to prove P is equal to NP, but in doing so they've gone outside of the theoretical bounds of the problem. And the problem is that you have to exist a deterministic Turing machine. That's all you have to do. One. Okay? It doesn't have to be in real life. It just has to be a DTM. The easiest way to do that. Not the most tractable solution, easiest to implement in real life because you need lots of disk. The easiest way to do it is just to say, I have a rainbow table. I'm going to query it in polynomial time. This is the answer. It has the answer if it exists. If it doesn't exist, it's going to reject in poly time. That's all you have to say. It's all you got to do. It's not hard. Tell Clay Maths.